Okay, now I wanted to go to some graphs here. Excel graphs, okay. Yeah. All right, where is it? Let's see now. Okay. Oh, wait a minute. Actually, here's one I didn't show. Now that I'm thinking about it. While I was on alkylation. This gives you a feel on the alkylate. Let's switch our minds back to the alkylate. This shows the effect of residence time. There's one factor you should get used to. LHSV, liquid hourly space velocity. It's basically a reverse of residence time. Like any reaction, the longer you give it, the more it reacts. So this is showing the effect of the octane you get out based on the acid strength. And as the acid strength goes down, of course, the octane goes down. And this is the opposite of residence time. So as residence time goes down, also your octane goes down. So you have to decide what residence time you want to give it in the reactor, and how far do I let my acid go down. If I try to keep it way up here, I'll consume more acid, and that's an expense. And if I put less, to get more residence time, if I put less rate through there, I'll also make less money. So it'll be an economic balance as to where I let my acid strength drop to, and how much I'll put through, how much barrels I'll put through. So somebody in economic planning, those are the money boys in the refinery, they'll decide where you're going to run here. Run at an acid strength of this and put this many barrels through it. So that's one that I had on alkylation that I didn't touch on. So okay, let's look at a couple graphs on reforming now too. Let's see, where's that? Okay. Seven. Okay, so I got a couple graphs here to look at. First one, the effect of the catalyst. This will show a little bit of history, just like on FCC, just like hydrocracking. Here's how the catalyst changed. They started with a straight platinum, then they started added rhenium with a certain formulation, and then they improved the formulation. So this is how much good it did for this process. With the old monometallic catalyst, you got 6 months maybe, and that ended your run. Then this bimetallic came out with rhenium on it. My God, all of a sudden you went 4 times as long. The same, that's called severity. The temperature you operate will be called the severity. So then finally they improved that a little more, and you end up getting more than 3 years on a run. So actually the savings, if you consider a shutdown is probably 10 days, here you had to do 4 shutdowns before this one needed a shutdown. Well, just saving one 10-day shutdown is about $1 million. So improving that catalyst did some pretty good. That's on a 10,000 barrel plant, which is a pretty small reformer. So millions of dollars. The catalyst improvements led to millions of dollars of increased profit. So okay, that's that one. And let's see here, what else? So yield's very important, of course. The more gasoline you get, the better. So this shows the effect of, let's see here. Now the other thing, they not only improved catalysts, but as they did that, the pressure came down. Those old catalysts operated about 500 pounds. And as they improved the catalyst, they lowered the pressure. And this is thermodynamically the way you want to go. The lower the pressure, the better for this reaction. So that's one of the main things that improved it. And you can see what happened here. over the years, 13 to 15% improvement in yield. That's equivalent to about $5 million more product for a 10,000 barrel plant. So by lowering the pressure. Now these new continuous reformers run about 80 pounds or maybe even a little lower. So that's been one of the trends: better catalyst and lower pressure. And that's kind of what it did for you. So, feed sulfur, very important. That's why you have to get it down. If you would allow it to get up to a whole 2 ppm, you would cut 25% loss in cycle life. So that's probably worth, you know, millions of dollars over a few years too. So what's important there is your NHT ahead of it, your naphtha hydrotreater ahead of it. Very important to get down in this range here to where you have no effect on cycle life and a little bit on yield too. So most of them will get you down to half a ppm, and a lot of them I've seen are 0.1, 0.2 ppm. So that unit's very important ahead of the reformer. All right, and now a little bit about hydrogen production. Once again, the same old thing, that increased catalyst and lower pressure has made a lot more hydrogen. So, which is, of course, you want in the refinery to utilize. And so for a $10 million plant, these improvements here from there to there give us about 7 million standard cubic feet more of hydrogen a day, and that's on a 10,000 plant, so that's a pretty small plant. So that's worth quite a bit of money. I mean, that much hydrogen. So another thing that's happened with our improvements in catalyst technology. Okay, this one here would be the deactivation rate. Once again, with the old catalyst versus the new, that's kind of what'll end your run. You know, your C5 yield used to just drop precipitously. Now, then the newer first generation bimetallic catalyst had your big improvement, and then improvements still beyond there. So it's a visual of, you know, improvements that have been made by research. Okay, let's see. I guess we'll go back to the other one, 7. Okay. All right. Now, so that's the fixed bed catalytic reformer. Let's look at a newer one here, the continuous CCR, UOP's process. I think, what's that French outfit? They may have one too. Not Technip, the one who owns Technip. I forget their name, but anyway, primarily it's a UOP process. They've sold pretty much all the CCRs. In fact, I don't know if you guys know Dan, but Dan's started a lot of these up for UOP. When he worked for UOP. Just like I started up a lot of hydrocrackers, he started up a lot of these CCRs. And it's kind of an FCC version for a reformer, you know, ability to continuously circulate your catalyst and regenerate it online. And so basically it works the same way. You know, you got to heat it up and everything, but it'll go through a 3-stage reactor, and meanwhile there's a let's see, the catalyst is moved. It's not exactly fluidized like a catalyst FCC, but it kind of flows through here, through some lock hoppers, and then gets lifted up by some air, so it's fluidized to some extent, into a regeneration zone. And actually there's a coke burning part to it, and there's a reduction part too. You actually have to change the form of the metals on the catalyst. It probably sulfides or gets some carbon on it, so you do a reduction phase with hydrogen actually and get it back to the base metal, the base platinum rhenium metal. So anyway, it regenerates it, does a lot of things, you know, a lot to that, but that's basically what it does. So anyway, it ends up back in with the, you know, coming back into the process here, and pneumatically transferred from here back into the reactor. So circulating catalyst and similar type reactors, but with fresh catalyst all the time. Now, what does this do for us? It ends up, you can run a much higher octane. The severity, there's a term called severity that you run these at, and you can run reformers at 95 octane, RON, or research octane. These units allow you to run about a 102 octane. One hell of a boost. I mean, 102 versus 95. So you run them much more severely because if you tried to run the fixed bed that way, you'd shorten the cycle to 6 months. But now, since you're continuously regenerating, now you can run real hard. You can run 102 octane. So that not only is better reformate, but it's a lot more hydrogen too. So the hydrogen coming off of here, there's a lot more of it, and it's much higher purity. And the purity doesn't decline like it did in the fixed bed reformer. It runs about 90–95%, so much better hydrogen. And so there's a lot of advantages to the process. It's not cheap, like anything, you get what you pay for. So once you eventually go to your recycled gas and your stripper once again, and make your reformate, the distillation part's pretty much the same as always. So anyway, that's the CCR process, and we almost put one in New Zealand, didn't we?
Almost.
And then they chickened out, didn't want to spend money. It's cheap, they're so damn cheap, they never want to spend anything. So they wouldn't put that in, and then Caltex wouldn't put the hydrocracker that I wanted to put in. So these guys are too cheap. We'd have a lot more work if they wouldn't be so cheap. So anyway, they didn't put it in. I don't know how the economics were. Did you ever see them? Or?
How much it actually, it was the most, it was the highest cost for the whole.
Oh yeah, I'm sure of that. So, but they may not be a real heavy gasoline maker. That may be the problem. A lot of the refiners over there tend to be mid-barrel refineries. They're more into diesel, and that may be why they didn't do it. Here, I think anybody that's gone in with a new reformer has gone in with a CCR, because for gasoline, it's hard to beat. And
I think they're thinking to put it later in the future.
Later in the future, which probably never, but okay. I've heard a lot of laters in my career. It's usually never. So, okay. Actually, here's the last slide. I'll just, yeah, go ahead.
Is that the process that you were describing, which is an alternative to the use of acids?
No, not really. That's alkylation, which would be combining C3, C4 olefins to make a C8. This is taking what's already a C8 and just driving out the hydrogen. So to make better octane. So they're totally different processes. Let me just show this last slide here. It's kind of how you troubleshoot these in a refinery. You won't see a slide there because it wouldn't come out right. I don't know. It wouldn't print right. I don't know why. But these softwares are all kind of interfering with each other. But I mean, as a process engineer out there, you'll be watching these things all the time. You see a decrease in the gasoline make. It could be that the chloride promoter is not the right amount. So you'll always be measuring that and adjusting your addition of chloride promoter. And usually it's just perchloroethylene, the same thing you dry clean your clothes with. So, and you might see a decrease in hydrogen yield. And sulfur poisoning will cause a lot of things. Decrease in the hydrogen yield, purity, decrease in reactor delta T. That reactor delta T is a measure of the work you're doing in it. So if that goes down, you know something's wrong. And if the recycled gas density or purity goes down, once again, sulfur can be the cause of all that. And another thing that can cause delta T to go down in a hurry is some metal poisoning. So, and some other things can happen. As I mentioned, low chloride, nitrogen poisoning because the NHT isn't working right. Feed bypassing reactors, sometimes there'll actually be leaks in them, and well, you have feed effluent exchangers, and you got to watch that on all these processes with feed effluent exchangers. If they leak through, you'll be leaking through feed into the product, and obviously that's not good. And when you start to see things fall off like this, one of the first things you'll start thinking about is you're leaking your feed effluents, and maybe you put a tracer in, you can see it. Put a tracer in, and if that tracer comes over in the product, then you know you're leaking. So it's something you're watching all the time. Bed channeling, sometimes if you didn't, you had an upset, you might have a little channel through the bed where stuff isn't contacting catalyst. And you're always watching reactor delta P too, because as it goes up, then you're wasting a lot of your energy, and that can be just scale accumulation, and a lot of times you want to put a filter in to prevent that. So anyway, that's reforming, and pretty much. So we pretty much handled gas. I'll tell you. Let's do one thing real quick. I did have those slides on. Let's see. That was the C7. C6? No, let's see. That it? Yeah, okay. I've got these 3 slides on blending. So we've made all these gasoline streams. How do we blend them up? And here's the things you have to consider blending. Read vapor pressure. Air quality people have wanted to limit that because at the gas pump, it all goes into the air. And a lot of the pollution came right from the gas station where you were filling up. And so now increasing RVP makes it easier to start in the winter and easier to vapor lock in the summer. But the main reason they've limited it is because of pollution reasons. Octane's what you really blend to. Research and motor are different. One's sort of a lightly loaded. Research is done at idle and under light load, and motor is done at heavier load and higher RPM. So we go by this for our octane. Now Australia just goes by R. I think ours is a better method because motor is pretty important. So, and the reason you want octane is to prevent knock. Another thing they'll watch is bromine number when you're blending gasoline. That's a measure of olefins basically, and they call it bromine number because the test dissolves it in some bromine chemical, and olefins somehow dissolve easier. So now the reason you don't want a real high bromine number or high olefins is they react in the atmosphere, and also they make gum in your tank. And if you have a lot of olefins, they tend to polymerize and plug up your fuel system. So they'll limit bromine number with the blend. Gum, which comes from that, they'll actually measure that. And diolefins, butadiene's real bad for that. So that one process I showed you removed butadiene. An endpoint, that comes from the distillation. And higher endpoints have more carbon, so they make more NOx, burn hotter, make more NOx, more particulate. And more and more they're limiting the endpoint. It used to be 430, then 400, and 380. Now it's down around 350 and tending to get lower. So it's cutting the top off the gasoline. And so that's got to go somewhere. You're not making money on that, so it's cutting into your profits. Some of it goes into jet fuel, but there's a limit to what can go there too. So all this cuts into their profits. So okay, let's go to the next one here. What else we got on? I guess I can make it bigger too. Here's just basically some specifications. These may be a little old by now, but this is still pretty much the same. Hardly anybody makes leaded anymore. I think there's a few places left, though, over in the countries, third world countries. I think this has gone down now to more like 7.5 in the summer and probably 11. That's an RVP. It's like a vapor pressure, but they do a test in the true vapor pressure, so it's TVP or RVP. TVP is hard to measure in the lab, so they have this test that measured. It's called the Reed test. So anyway, those are the limits on that. Bromine number. No Now, it's not limited most other places, but in LA it's limited, so that'll limit your olefins and how much FCC gasoline you can put in there, and pretty much throws out the polymerate that people used to use. Endpoint max 437, that's probably down more like 380 now. Sulfur, okay. Yeah, that's what it used to be. Now it's down around 15, so I probably need to upgrade this chart here. So these are the specifications, and you can get them a lot of different ways. I mean, it's not a constant formula like 20% reformate, 30% alkylate, or anything like that. There's a lot of different ways you can achieve these, goals here, these specifications, and they're getting tighter all the time. Okay, here's the last one here. Make that one a little bigger. So here's the streams you'll blend with. Straight run from a crude unit. Doesn't have great octane. It's cheap though. You didn't do anything to it, so you'll get put all that in there you can. But it also has a high RVP, so it's limited how much you can get in there. And endpoint's pretty low, so gum's low. Okay, reformate, basically pretty high value. They've had to cut this endpoint. So there's the main advantage. RVP is fairly low, high octane. FCC gasoline, a little lower octane. Bromine number's a bit high. There's the problem. That's what limits you from using too much FCC gasoline. And RVP is okay. Polymerate's been thrown out pretty much because of bromine number, as you can see. But good octane anyway. Light hydrocrackate, octane's kind of low, so you don't use too much of that. Usually goes to the reformer and makes that. Alkylate, that's kind of the perfect one. High octane, and actually you can lower that RVP. No bromine and no low gum, so very few negative factors for that. Butane, you used to shove all the butane in there you could, but with that, now the RVP down, you can't get much in. It had good octane and was cheap, so, but anymore with RVP you can't get it in there anymore. Low gum, so it was a good one. MTBE, been banned already. So great stuff, 110, 105. So, but we had to take that out. I'm still not quite sure why. Leaks in the groundwater, a little on the toxic side. I guess maybe that's it. I mean, ethanol is going to leak into the groundwater too, but that's not toxic. You can drink that. So, and actually, that methanol too is real high octane, but probably be more like methanol. Take the M out of there. So anyway, that's kind of the things you have to blend, and there's a lot of combinations that will get you those specs. But there's all the streams anyway. So, any questions or anything? Okay, I guess we're done then.
Thank you very much.